Okay, so continuing our related rates problems, here are some more examples. We've already done a couple. Here's the next one. It says water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? Okay, so identify all of the variables in this problem. Water is leaking out of a cylinder, so we have volume for sure. Our volume is being affected. Okay. It talks about the radius. It tells me the radius. And it is asking me to find the change of the depth of the water. The depth of the water is the height. Okay. So when we think about a cylinder, how high is the water at any given moment? Okay. Number 2, identify which, if any, of the variables in the problem remain constant. Well, we know the volume is not staying constant because the water is leaking out. We know that the height is not staying constant, the height of the water, right? That's what this height is talking about. The height of the water is not constant because it's going down as well. But the radius, it doesn't tell me that the radius is changing. And if we're talking about a cylindrical tank, we would hope that the radius wouldn't be affected by the water coming out. Okay? So the radius of this tank is staying constant. And it tells me it stays at 4. Okay. Number 3, identify the rates that are given and the rate that we wish to find. Well, these rates are for the remaining variables that were not constant. So we know we should have a rate for the volume, and we know we should have a rate for the height. Okay, so I know I'm going to have dV dt and dH dt. Okay. dV dt, they say that it's leaking out of this cylindrical tank at a rate of 3 cubic feet per second. Thinking back to that problem we worked on in the last video, because water is leaving this tank, our rate is negative. Okay. And then dH dt, that's what it's asking me to find, is what rate the depth of the water is changing. And that would be in feet per second. Okay. So what's an equation we can use to relate all of our variables? Almost always it's going to be your formula for volume, especially when we're talking about a volume problem like this. So this would be the volume of a cylinder. The volume of a cylinder is pi r squared h. Okay, but now remember how I highlighted before, we want to substitute any value that represents a variable that is constant at this point. Okay, we know that the r is constant and it stays at 4, so I want to plug 4 in for r now before I do the derivative. Okay. So it's 16 pi times h. Okay. So now 5, we want to differentiate both sides, but the reason I wanted to plug that 4 in before this step is so now I don't have to deal with r when I'm doing the derivative. I can just worry about v and h. So the derivative of v is dv dt. And then that 16 pi is a coefficient for h. So the derivative of 16 pi h is 16 pi times dH dt. Okay. Number 6, substitute all instantaneous rates and values and solve for what's remaining. We know what dV dt is. It's -3 then 16 pi dh dt. Divide both sides by 16 pi, and you get dh dt equals -3/16 pi feet per second. Okay. Moving along. Next problem, a cone has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing with a rate of 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changing? Okay, let's draw a really quick picture here, because this is kind of an involved problem. So we're dealing with a cone. I'm going to draw it kind of to the side here. So we have a cone, and water is being poured into the cone. So I'm going to draw the level of my water there. Okay. The radius of a cone is not always constant, right? That's why it's saying that the we want to find, or I mean, it says that the instant when the radius of the exposed surface area of the water is 2 inches. It's saying at the instant when it is this value because there are different values of that radius, because the radius of a cone changes as you go up and down. Okay. So the radius at the top is different than the radius at the bottom. But we are going to represent radius with r. Okay. That line that I just drew down the center, that is the height of our cone. Okay. The height of our cone and the height of the water are different. So it tells me that the water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second, not the height of the cone. So the height of our water level only goes to that point there. Okay. So now I kind of have an idea of what this is looking like. What are the variables that are involved? Well, definitely the radius and the height. Okay. And then it's asking me to find the rate at which the volume of the water is changing. So volume is also a variable here. Are any of these constant? Well, the height is changing of the water level. The radius changes because we have a cone. And the volume is changing because the water level is increasing. So there are no constant variables. Okay. Identify the rates that are given and the rate at which you wish to find. Well, we know the rate at which the water level is changing. That's dH dt. Okay. And the rate at which it's changing is 1.2 inches per second. They want me to find the rate at which the volume is changing, which is dV dt, which is inches cubed per second. Now you guys might be thinking, radius is not a constant variable, and they didn't tell me anything about the rate at which the radius is changing. We're going to deal with that in a second. Okay, so now let's come up with the equation that relates all of these variables together, and we're going to include r for the moment. Okay, so the equation that I would want to use is my volume equation. Volume of a cone is 1/3 pi r squared h. Okay. But just like I said, we have r in our equation. I don't want to differentiate with r in the equation because then I'm going to end up with dr dt, and we don't have a dr dt, and we don't know how to find dr dt. okay? So I need to come up with some other kind of relationship with r and my cone so that I can figure this out, okay? The very first sentence is where we get this relationship. It says a cone has a diameter of 10 inches and a height of 15 inches, okay? So on the side here, I'm going to do a little bit of work and draw my line here, okay? So we know the diameter and the height have a relationship, a ratio of 10 to 15. Okay, the diameter is 10 when the height is 15. Well, I can use diameter and help me find the radius, right? The diameter is 2 times the radius. So this tells me that the radius in relationship to the height is 10 divided by 2, which is 5 to 15. So simplify that fraction. The ratio from radius to height is 1/3. And this is a constant relationship, okay? So when the height is 30, okay, the radius is 10, and so on and so forth. Okay, this is a constant relationship between that radius and the height of this cone. Okay, so now I'm going to use this to help me replace r, because I can get this equation solved for r. Actually, I'm going to write it a little bit smaller. I kind of didn't give myself a whole bunch of room there. Okay, so we said r to h is 1/3. If I multiply both sides by h, r is 1/3 h. Okay, I'm going to plug that into r for my volume equation. So really this is volume equals 1/3 pi. Instead of r, I'm going to put 1/3 h squared times h. So now I don't have r in my equation at all. I'm not going to end up with dr dt when I take the derivative. Just clean this up a little bit. Volume is 1/3 pi times 1/9 h, and now it's to the 3rd power because we have h squared times h. So lastly, 1/3 times 1/9 is 1/27 pi h to the 3rd. Okay. So now I can differentiate both sides, and I will have variables and rates that I actually know what to do with. So the derivative of v is dv dt, and then the derivative of the right side, 1/27 pi, acts as a coefficient. So I take the 3, the exponent 3, bring it out front and multiply it by that. I end up with 1/9 pi, and then h squared now instead of h to the 3rd times by dh dt. Okay. Step 6, plug in what we know. We know that dh dt is 1.2. I know that the height that it's asking me, I can find out because they tell me the instant the radius is 2. Okay, so what do we know here? I'm trying to find dv dt still. I know 1/9 pi. I'm going to come back to this h in just a second, but dh dt is 1.2. Okay, the information they gave me was that the instant the radius is 2. Well, I know a relationship between the radius and the height. My relationship between the radius and the height is r is equal to 1/3 times the height. If the radius is 2, then h must be 6. So I'm going to plug that in for h. So dv dt is equal to 1/9 pi times 36 times 1.2. So dv dt is about 4.8 pi inches cubed per second. So we had to do a little bit manipulation here. So that italicized part on number 4, it says it is important to keep in mind that you can have only one more variable than you have rates. So in this case, when we had R, we had 2 more variables than we had rates. We only had dH dt. So you may have to make the substitution that relates one variable in terms of the other, which is exactly what we did with R and H. Okay, moving along. Next we have a ladder that's 25 feet long leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Part A asks how fast the top of the ladder is moving down the wall when the base of the ladder is 7 feet from the wall. Draw a picture. If it's a situation where you are able to draw a picture, draw the picture. So we have a house. I'm just going to draw the edge of the house. Okay. That is my house. We have a ladder leaning up against the house, like so. Okay. And they tell me that the ladder is 25 feet long. Okay. Circle, highlight, underline important information because we don't have that organizer here on this problem. Okay, they tell me the base of the ladder is pulled away at a rate of 2 feet per second. Okay. And they want me to find how fast the top of the ladder is moving down the wall when the ladder is 7 feet from the wall. Okay, so I need some variables here. I'm going to call the distance from the bottom of the house to the bottom of the ladder, I'm just going to call that X. And the distance from the ground to the top of the ladder, I'll just call Y. And I added those to my picture here. Okay. So from what I have boxed in from my problem, the 2 feet per second, that's the rate at which the bottom of the ladder is moving away. That is dx dt. And when the base of the ladder is 7 feet from the wall, that means that we're looking when x is 7. So what are they asking me to find? How fast is the top of the ladder moving? That's dy dt, because that height from the ground to the top of the ladder is y. And that's what's changing when the ladder is sliding down the wall. Okay. So I need to, if I'm following this graphic organizer, okay, all the variables we have, we've kind of already identified x and y. Those are the variables that we're talking about here. Which of the variables are constant? None of them in this problem are. Identify the rates that are given and the rates we wish to find. We know we have been given dx dt and we want to find dy dt. Okay, so now we need an equation to relate them together. Okay, we need an equation to relate x and y. Okay, when we're dealing with a ladder leaned up against a house, what shape did we just form? Well, we formed a triangle with the house and the ladder and the ground. So I'm going to use the best equation known for a triangle of this kind. This is a right triangle. I want to use Pythagorean theorem. I know that x squared plus y squared is equal to 25 squared. Okay. I can now differentiate both sides here. The derivative of x squared is 2x times dx dt, plus the derivative of y squared is 2y dy dt, and then the derivative of 25 squared is 0. Okay. So substitute what I know. I know that x, we're looking at when x is 7, and I know dx dt is 2 feet per second, plus 2, I don't know what y is, but I can find it. And then dy dt is what I'm trying to find. so I'm going to leave that as dy dt. So you notice that we still have one blank here that we need to fill in, that y value. So this y value is when x is 7. So when x is 7, the hypotenuse, the ladder is 25. I can figure out what y is by using the Pythagorean theorem. I'm going to do that work off to the side here. So we have when x equals 7, okay, then x squared plus y squared equals 25 squared will really look like 7 squared plus y squared equals 25 squared. And I can get y by itself. So y squared is going to end up being 576. So y is 24. And that's what I plug into my differentiated equation. So now I have 2 times 7 times 2 is 28. Plus 2 times 24 is 48, dy dt. I forgot to write equals 0 here. Get dy dt by itself, so 48 dy dt equals negative 28. So dy dt is equal to negative 28 divided by 48, which is negative 7/12. And this rate is in feet per second. Okay, so that's part A. Part B, consider the triangle that's formed by the side of the house, the ladder, and the ground, which we were just using. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Okay, so now instead of finding the rate at which the height the ladder is up the house is changing, we want to find the rate at which the area of the triangle is changing. Okay. And we're still when the base of the ladder is 7 feet from the wall. So this is still x is equal to 7. I'm going to draw that triangle again here. So still x and y and 25. Those numbers are still the same. But now I want to find dA dt. Okay, so our variables are still the same. The only one we are introducing now is area. I still have x and y though. Okay, none of these are constant, and so now we just need an equation to relate them. So if I'm dealing with area, I'm going to use the area of a triangle formula, which is 1/2 base times height, which is 1/2 xy. Okay, now I'm going to differentiate both sides. So dA dt is equal to, this is a product rule again. So we have 1/2 x and y. Those are the two things being multiplied together. So the derivative of 1/2 x is 1/2, and then dx dt times y, plus the derivative of y is dy dt times x. Times 1/2 x, sorry. That first part, that 1/2 is a part of that. Okay. So now we can fill in what we know. We're trying to find dA dt. 1/2 stays the same. We know what dx dt is. Dx dt is still 2. And we know what y is. We found y in part A was 24, because we're still looking at when x is 7. If they changed that to be a different number, we would have to find out what y was again. But since x is staying 7 feet from the wall, that can stay as 24. plus dy dt we found in part A, times x is 7 times 1/2. So dA dt, 1/2 times 2 times 24 is 24. Plus negative 7/12 times 7 times 1/2 is negative 49/24. So if I put this in my calculator, dA dt is 21.958 feet squared per second because it's area. Okay. Finally, part C. Find the rate at which the angle formed by the ladder and the wall of the house is changing when the base of the ladder is now 9 feet from the wall. Okay, I'm going to draw myself another triangle here. We have our triangle, x, y, 25. Okay. Find the rate at which the angle formed by the ladder and the wall of the house is changing. Well, the angle from the ladder and the wall is the top one up here. And I'm just going to call that theta. Okay. And now it's asking when x is 9 feet from the wall. So I'm going to have to figure out what y is again. Okay. Just like I did in part A, I'm going to use the Pythagorean theorem. So when x is 9, what is y? Well, x squared plus y squared is still 25. So 9 squared plus y squared is, oh, I forgot the squared there, 25 squared. So y squared is 544. So y is just the square root of 544. Okay. So the rate at which the angle formed is changing, that is d theta dt. What rate is theta changing? That's our new variable here. We still have x, we still have y. In part B, we added in the area as our new variable. In part C, our new variable is theta. Okay, so I need a relationship between theta, x, and y. I need a relationship that combines all of them, or at least two of them. Okay, specifically, I want x and theta because they tell me when x is 9. I could use, now that I know what y is, what that is, I could use that relationship, but because they told me what x was, I can use the relationship between x and theta, x, theta, and y, or y and theta, because I know the hypotenuse. Pretty much this boils down to our trig identities, okay, SOHCAHTOA. So I'm going to use sine theta. What's the relationship for sine of theta? Well, sine is opposite over hypotenuse, so that's x over 25, which is the same as 1/25 x. Okay. Differentiate both sides here. The derivative of sine theta is cosine theta. And then times d theta dt. Don't forget that part because theta is our new variable. The derivative of 1/25 x is just 1 over 25 times dx dt. Okay. Cosine theta, because I don't know what theta is, they didn't tell me what theta is, I need to do what we did with that radius and height back in the first video, okay, or back in a previous problem. I don't remember which video it was in. I need to figure out cosine of theta as a different kind of relationship. So cosine of theta is our adjacent over hypotenuse. Well, we know what the adjacent is. The adjacent is y, which is now the square root of 544 over 25. That's our adjacent over hypotenuse relationship. So I'm going to replace that here just so I don't have to deal with theta. Okay, so the square root of 544 over 25 times d theta dt equals 1 over 25. I know what dx dt is, it's still 2. You could have done this problem with any of the trig functions. Okay, we know our opposite and adjacent sides. So if I didn't want to do sine at the very beginning, I could have done cosine, or I could have done tangent. Okay, I could have done any of those because I know all three sides of my triangle. I just picked sine. Okay, so now we want to solve for d theta dt. So d theta dt, get rid of that square root 544 over 25 by flipping it and multiplying it on the other side. So 2 over 25 times 25 over the square root of 544. So d theta dt, those 25s are going to go away. I'm going to flip 2 over the square root of 544. And remember, calculus is always in radians per second. Okay. All right. This last one, I'm going to just post the notes for. You guys can try it on your own, check your work on the notes. I'm not going to do it in the video, but if you need me to explain it to you further on Zoom or with an email, just let me know. But I'm going to stop